In this video, we will conclude our review of the central limit theorem, and we will look at a historical note in the sense that we no longer need to use this method since currently we have technology that pertains to finding binomial probabilities. A long time ago, when technology was not available, binomial probabilities had to be computed by hand. That included the very difficult binomial formula and powers of probabilities that are decimal numbers, and when n was too large, very difficult and lengthy calculations for the combinations n choose k. So instead of doing this, statisticians at the time were approximating a binomial probability using a normal distribution. To do so, you have to have a very good approximation for your binomial probability, so a lot of things have to be in place. First of all, you must have a binomial experiment, which means a fixed number of trials, only two outcomes, success and failure, and independency that maintains the probability of success p, all the same in every trial. If that is the case, then your variable will follow a binomial distribution with n repetitions and probability of success p. And if you want a normal distribution to approximate your binomial distribution, then you have to ensure that n times p and n times q is larger than 5, but ideally, for a better approximation, greater than or equal to 10. And if you remember from our formula packet for the midterm exam, a binomial distribution has a mean of n times p and a standard deviation of the square root n times p times q. If that is the case, then your binomial can be approximated by a normal distribution that has the mean of your binomial distribution, and standard deviation, the standard deviation of your binomial distribution. Because the normal distribution refers to a continuous variable and the binomial distribution refers to a discrete variable, we use something called the continuity correction factor, which is 0.5. And what happens is, when we are calculating probabilities in a discrete variable, the probability of the value of the variable to equal the value x exists. It's the area of one of the rectangles centered over x. So if I have these discrete values of my variable and the rectangles in the binomial probability are centered over x, if I want to, let's say, calculate the probability of being greater than a particular value, let's say this one, then I will not include this rectangle, but I will include this rectangle and everything else to the right. If I want it to be greater than or equal to a particular value of the variable, I would include the rectangle of the variable and then everything to the right. For the normal distribution, the best approximation would be to either go half a point above to the border of the rectangle on the right, or half a point below, and then start calculating probabilities. In the case of probability x greater than this little value of x, I will want to go half a point above. If I wanted to calculate the probability of x being greater than or equal this little value of x, I would have to go here, which is half a point below. So this border of the rectangle that is centered at x has a left bound of x minus 0.5 and a right bound here of x plus 0.5. And then every whole number is centered under every rectangle. So when you are embedding a continuous curve here, you want that continuity to be as close to the area of the binomial distribution as possible, and that's why we use the 0.5 continuity correction factor. So in an example below, we do have the technology for binomial distribution, so we will use them both. We will use both the binomial distribution and the normal approximation to answer the questions and to compare the solutions. So suppose in a local kindergarten through 12th grade school district, 53% of the population favor a charter school for grades K through 5. A simple random sample of 300 is surveyed. So I have n equals to 300, p equals to 0.53, and q equals to 0.47. I assume that the decision between members of the school district is independent, so that it's always 53% chances of favoring the charter school. Can we actually approximate this by a normal distribution? I want to check that NP, which is 159, that's the 300 times 0.53, is greater than 10, which is a check, and NQ, which is 300 times 0.47, and this is 141, is also greater than 10. That's another check, so the answer is yes. If that is the case, what is the normal distribution? Well, the mean of the binomial is 300 times 0.53, which is 159. So the normal distribution will have a mean of 159, and the standard deviation is square root of 300 times 0.53 times 0.47. This is the square root of 74.73 when I do it in my calculator, which is approximately the square root of 74.73 is approximately 8.645. And the first question that I'm going to do in both binomial and normal distribution asks me to find the probability that at least 150 people in the district favor the charter school. At least means greater than or equal to, so at least 150, I'm looking for the probability x is greater than or equal to 150. And I'm going to do that with a binomial distribution and with a normal distribution, and I will use functions in Excel for that. I want to remind ourselves how Excel works with the CDF. The CDF in Excel calculates probabilities less than or equal to your value. So it will, if I wanted less CDF for 150, I will be calculating the probabilities from 0, 1, 2, 3, etc., to 150. If they are asking me for the probability that x is greater than or equal to 150, then I am looking for the probability of 150, 151, 152, 153, etc., up to 300. Therefore, if I wanted to use CDF, I will need to do CDF from 0 to the value below. And from 0 to the value below 150 equals 150 minus 1 for a discrete variable, which will be 149. So when I calculate when I use binomial CDF in Excel, I will have to find the probability from 0 to 149 and then subtract that from 1 to find the probability from 150 to 300. So let's write here our values. We have n equal to 300, we have p equal to 0.53, we have q equal to 1 minus p, the mean equals n times p, and the standard deviation equals the square root of n times p times q. And correctly, you can see it is approximately 8.645 as I calculated in my calculator, and the mean is 159. So my numbers over here are correct. I'm in good shape. Let's try to use binomial CDF from 0 to 149 to find the answer for the probability x greater than or equal to 50. So this is going to be 1 minus binomial distribution. What is the number of successes? I want it to be the 49, not the 50. I want the 50 to be part of my answer, not the part of the CDF that gets excluded, comma. What do you want your trials to be? I want it to be 300. I'm going to try to keep this steady. It's always going to be in location C3, so I'm going to use dollar signs. What's the probability of success? This is here, and again, I'm going to try to keep that steady as I copy. So $C and $4, it's always going to be in C4. And do I want it to be cumulative? The answer is yes, I do want it to be cumulative. So the answer here will be 0.86407. So in Excel, 1 minus binomial CDF, and I had the number of successes to be 149. I had 300 repetitions, 0.53 and true, for indeed calculating a CDF and adding all the probabilities from 0 to 149, and that came out to be 0.8641. But if you round it is 8641. And then I'm going to use the normal distribution. It's the same thing. We didn't use it in project 5, but we can use it now. So the normal distribution will do the same thing. If I want to calculate the probability from 150 going up, then I will want the rectangle of 150 to be included, and therefore if this is the rectangle for 150 and I need in a continuous curve for that area to be included in the probability x greater than or equal to 150, I will want from here all the way to the right of the normal distribution the probability to be included. But that means that I want this number to not be 150 but to be 149.5. So I need to know the border of that rectangle to the left. And the border of that rectangle to the left is equal to this number minus 0.5. And I want this to be included in the probability. So therefore, I want to calculate the probability for the normal distribution up to 149.5. So when I will do the normal CDF, I will do it up to 149.5, and then from 149.5 to the right, it will be the probability of x greater than or equal to 150. So if I do equals 1 minus and then use the normal distribution, the normal distribution says, what do you want the value of x to be? And I want for the CDF to be 149.5. What do you want the mean to be? The mean will be the mean of the binomial distribution. And again, I want to keep it steady, always be at C7. What do you want the standard deviation to be? I want the standard deviation to be over here, and I want it to always be at C8. And do you want it to be cumulative? Yes, I do. I want you to calculate all the probability from 0 to 149.5 and then subtract it so that I can have the area from 149.5 to the right. And this answer comes out to be 0.8641. So 1 minus the normal CDF, I used 149.5 because this is now a continuous variable. The mean was 159. The standard deviation was this 8.645. And I did want the CDF because I wanted the probability to the left to be subtracted from 1. And that came out to be 0.8641. And they were very close to each other. The next question is, find the probability at most 160 will favor the charter school, and that at most means less than or equal to 160. This is a direct binomial CDF. And since 160 is included, it will just be 160 with the same parameters as before. So if I write here 160, when they want at most 160, they want all of these values to be calculated, and this is the binomial CDF. So let me copy the binomial CDF here, and if I just paste it, I don't want G5, I want this number to be the 160, and the mean and the standard deviation and the number of repetitions and the probability of success to be 0.53, and it is a true statement, so yes. So my answer here will be 0.56842. And now if I want to do that with a normal distribution, which is a continuous distribution, let's sketch again what we are looking for. So we have this binomial distribution with the probability of being equal to each of the values. And this is the 160. And I want to calculate the probability of being equal to 160 or less. So I want all of these probabilities to the left. And when this becomes a normal curve, I want the probability from this border of the rectangle to the left. But this border of this rectangle is 160 plus 0.5. And then I want the area from 160 plus 0.5 all the way to the left. So that number is 160.5. So here in my Excel, I'm going to find this number. So equal to this plus 0.5. And then I'm going to do the normal distribution. I don't need to subtract it from 1 because the normal CDF calculates these areas from that point and down. And I just need to make sure that I have the correct data point. And the correct data point is this 160.5. And the mean is 159, and the standard deviation was the standard deviation of the binomial distribution. And this comes out to be 0.56888. And you can see here that again we are very close with accuracy to the thousandth, and very close again with accuracy to the 10,000th, approximately only 4 10,000ths away. Find the probability that more than 155 favor the charter school. So probability X being greater than 155. So if our number here is now 155, then let me actually copy these values over. We don't have the values that we need yet, but we will find them. So 155 greater than 155 will be 155 plus 1. So it will be from 156 to 300. So they're asking us to find this. And therefore, to find this in the binomial distribution, I will need to calculate the CDF from 0 to 155 and then subtract that from 1. So if I want to find the probability of 156, 157, 158 up to 300, I will need to find the probability from 0 to 155 and then subtract it from 1. So this here will be equal to 1 minus the binomial distribution, and instead of I7, no, actually I7 will work. I will need 1 minus this. So the answer for that is 0.65754. So 1 minus the probability of X being less than or equal to 155. And that answer came out to be 0.65754. And when I will do it with the normal distribution, so when I'm here, and these are the rectangles in the binomial distribution, and this is my 155. When they are asking me to calculate the probability of being greater than 155, I will need to add these areas over here to the right, and that value that is the cutout for the continuous distribution is 155.5. And remember that the normal CDF will find this area, normal CDF. I will need to subtract it again from 1. So I need to find the 155.5 over here, and I will want the CDF to go up to 155.5, calculate the area from 0 to 155.5, and then subtract it from 1. So here I want this to be equal to 1 minus the normal distribution from 155 down. And that comes out to be 0.65722. And again, as you can see, I am accurate to the nearest thousandth, and I have only 3 ten-thousandths difference. Find the probability that fewer than 147 will favor the charter school. So this is the probability that X is less than 147. In terms of binomial CDF, so if my number here is 147, less than 147 will be all these values. One below 147 will be 146. So less than 147 will be from 0 to 146. That is a binomial CDF. It just needs to make sure that it has 146 there and not 147. So here, that will be less than 146. 0.07421. So that will be the probability of x being less than or equal to 146 in terms of discrete variables, and that was 0.07421. In terms of a continuous random variable, if this is the rectangle for 147, and I'm looking for the probabilities less than 147, I'm going here. I am not counting this rectangle. So in terms of the normal CDF, I need this border for the area, and that will be 147 minus 0.5. So for the normal distribution, x less than 147 will be the probability of x being less than or equal to 146.5, and that will be the normal CDF with 146.5. So I also need this value, and that will also be calculated in my normal CDF. So here I need the normal distribution with the value of 146.5. And that was 0.07409. Find the probability that exactly 175 will favor the charter school. Let me see if I can fix the English here. All right. Exactly 175 will favor the charter school. So in terms of binomial distribution, 175 will be here. And I can find that value for the binomial distribution if I just say that I don't want it to be a CDF, I want it to be false. So 175. So I will do binomial CDF, and I'm gonna have false at the end. So let's see that. If my number here is 175, I will go here, and instead of saying true at K7, I'm going to say that I want it to be false, so that I only get the one value. So the probability is 0.00833. But when I use a continuous random variable, the probability of being exactly 1.175 is non-existent. So if I want the area of this rectangle in terms of a continuous random variable, I need to find the area of the normal curve from the left bound of it, which is 174.5, to the right bound of it, which is 175.5. And that's how I will find the area of the rectangle that is centered over 175. So here for the normal distribution, it will be the probability of x being between 174.5 and 175.5. If you are in Art of Stat, you will need to do actually do an interval, find the probability of an interval. But if you are using Excel, you have to get the area from 175.5 and then subtract the area here to the left for 174.5, and that's how you will find the area in between. So that will be the probability of x being less than 175.5 minus the probability of x being less than 174.5 when I am in Excel. And let's see how we can calculate that. So I need to add, so I only need this value, that will be my green one. And what I need to subtract a half and add half, and in Excel I'm gonna calculate this. So to calculate this in Excel, like I said, it has to be the normal distribution of 175.5 true minus the normal distribution of 174.5. So the CDF of 175.5 minus the CDF of 174.5. And the answer is very close again, 0.00833. Again, Art of Stat is much easier because we don't have to think how the CDF is used. In Excel, the binomial and the normal distribution only go from the smallest value up to your current value if you want the CDF, so you have to do math to calculate the areas.